Welcome to another lecture on signal and system. So let us do some problems related to LTI system and discrete time, continuous time LTI system and discrete time LTI system. I am Ravi Shankar from MITS Madnapalli. So the question is the step response ST of a continuous time LTI system is given by ST is equals to cos omega naught t into ut. The question is find out the impulse response HT of the system. Find out the impulse response HT of the system. So the solution of this problem is the step response is given, that is cos omega naught t into ut. So this step response is given. The impulse response, so the impulse response HT is basically the differentiation of step response. So the impulse response HT is nothing but d by dt of cos omega naught t into ut. So let us solve this. So cos omega naught t, the solution is cos omega naught t plus del into del t, because the differentiation of ut is del t, plus ut into minus sine omega naught t into minus omega naught. So the solution is we have del t multiplied by cos omega naught t minus omega naught sine omega naught t multiplied by ut. Now what is the product of this? The product of this is simply del t, because the delay is 0 here, so cos 0 is 1, and here what we are getting is omega naught sine omega naught t into ut. So this is our solution. So the impulse response HT is del t minus omega naught sine omega naught t into ut. Let us solve another problem. So the problem is the system shown. The system is given as the LTI system is given as the system. The system shown below is formed by connecting two systems in parallel. So that's the system is like this. This is our figure of, this is our system. So this is H1t and this is H2t, and here you have summation of these two H1t and H2t, and we are getting yt. This is summation. So the first part is, and what is h1t? What is h1t? So h1t is equals to e raised to the power minus 2t into ut. And what is h2t? h2t is 2 e raised to the power minus t into ut. This is h2t. So first part is find out the impulse response, find out the impulse response ht of the overall system. Next is the overall system stable? Is the overall system stable? So this is our problem. Now let us find out the answer. So HT is nothing but if the two systems are connected in parallel, and that is that impulse response HT is nothing but H1T plus H2T. So the impulse response. So basically, what I want to tell you that this is HT and this is H2T. This is H1T. This is H2T. If they are connecting in parallel and there is summation here, so that overall impulse response HT is nothing but H1T plus H2T. It is H1T plus H2T. So what is HT? So HT is equals to H1T. What is H1T? Is it 2 e raised to the power minus t into ut plus H2T. And what is H2T? It is given 2 e raised to the power minus t into ut. Now the second part is the overall system stable? For that we need to find out the integral minus infinity to plus infinity modulus of h tau d tau. If it is bounded, if it is less than infinity, if it is bounded, if it is bounded, then stable, otherwise unstable. So let us find out this. So minus infinity to plus infinity modulus of h tau is e raised to the power minus 2t ut plus 2 e raised to the power minus t into ut d tau. Now we can see that the solution of this is bounded. The solution of this is 0 to infinity e raised to the power minus 2 tau d tau plus 0 to infinity 2 e raised to the power minus tau d tau. So here it is tau. Please correct this. It is tau. Okay, because we have h tau we have taken here. So the solution is basically bounded. The solution is bounded. Please check, and it is less than infinity. So the system is BIBO stable. The system is BIBO stable. Why? Basically that impulse response is integrable. The impulse response is integrable because it is BIBO stable, because the impulse response is absolutely integrable, because the impulse response is absolutely integrable. That's why we can say that the system is bounded input, bounded output is stable. So let us do another problem. The problem is, consider an integrator. Consider an integrator Consider an integrator whose input xt and output yt are related by yt is equals to minus infinity to t x tau d tau. So first problem is find the impulse response st of the integrator. Find the impulse response st of the integrator. Second is the integrator stable? Is the integrator stable? So let us do this problem. So the solution is first is yt is equals to minus infinity to t x tau d tau. It is given. So if xt is equals to del t, then yt is nothing but ht, that is impulse response. So basically we can write it as yt is equals to transform system operating inside. If we are providing del t, then it is equals to ht. So ht is basically minus infinity to t h tau d tau, because we have replaced xt with del t. So it is minus infinity to t del tau d tau, and it is nothing but ut. So the impulse response is nothing but the unit step function. So this is the impulse response of the system. This is the impulse response of the integrator. Now let us do the second part. Let us solve the second part. It is if it is BI/BO is stable, then we need to find out the integral. So first we need to find out that integral minus infinity to plus infinity h tau d tau, and the solution of this integral is that it is equals to minus infinity to plus infinity modulus of u tau d tau. It is equals to 0 to infinity modulus of u tau d tau. It is equals to 0 to infinity 1 into d tau. So it is unbounded. So basically the integrator is not stable. The integrator is not stable because the impulse response is not integrable. We are not able to find out the integration of this impulse response. That's the integral of this impulse response, that it is not integrable, absolutely integrable. So let us do another problem. So consider a LTI system. It is discrete time, and the impulse response, consider a discrete time LTI system with impulse response Hn is equals to del n minus 1. Is this system memoryless? So the solution is Hn is equals to del n minus 1, since we are taking the delay. Since there is delay, so this type of system is with memory. So this is with memory. So it has memory, it is memory, it has memory. So the system has now a very important topic is system described by differential equation. So topic is system. Let us discuss this topic, system described by differential equation. So let us discuss some of the first, what is that linear constant coefficient differential equation, and after that we will see some of the properties of this linear constant differential equation. So let us discuss the linear constant coefficient differential equations. Okay, so a general nonlinear, nth order linear constant coefficient differential equation is given by summation k is equals to 0 to capital N ak d raised to the power k, that is k time derivative of yt with respect to t, plus equals to summation k is equals to 0 to capital M bk, then kth order derivative of xt divided by dt. So in this way we can represent the linear constant coefficient differential equation. So in this way we are going to present the linear constant coefficient differential equation. Okay, so let us discuss various parameters. So where coefficients ak and bk are real constants, these are real constants. So ak and bk are real constants, and the order n refers the length, refers to the highest derivative, that n refers to the highest derivative of yt. So yt is basically output and that xt is basically input of the system. So such differential equation, basically these differential equations plays very important role. Such differential equations play a central role in describing the input, in describing the input output relationship of a relationship of a wide variety of electrical, so the areas in which it is applicable, so it is electrical, then we have mechanical, and also biological systems. So let us discuss one of the example. Let us discuss one of the example. Consider a simple RC circuit. Let us discuss this. Consider a simple RC circuit. So the circuit is like this. We have a resistance R, and also we have a capacitor C. So this is our RC circuit, and let us apply an input, that is VST, and a current is there following across this circuit, and the voltage across this capacitor is VCT. So basically what we are going to do, let XT, the input is nothing but VST, that is voltage, in source voltage, that is source voltage. So the source voltage is basically the input, and YT is VCT, that is voltage across the capacitor. So we can write it as VST is equals to R into IT plus VCT. Now what we can do, we have already said that XT is equals to VST and YT is equals to VCT. So this equation can be written as, so setting VCT is equals to input XT, and VST is equals to the output YT. So here it is VST and this is VCT. So VST is nothing but the source voltage, and we are taking it as an input, and VCT is that voltage across the capacitor, and that is we are setting at output, okay, YT. So if we use these two relations in this equation, so if we use these two relations in this equation, so what we will get here, we will get XT is equals to RC D basically let us write it in this form. So we have RC DYT divided by DT plus YT is equals to XT. So just we have replaced VST with XT and VCT with YT. Now what we will get, and also we have used the relation, that is current is equals to C dVC divided by dt. So what is I? It is nothing but dyt divided by dt. So we have used this relation also. So we are getting this equation. Now further we can put this RC, we can divide both sides by RC. So by dividing both sides by RC, so what we will get? We will get d yt divided by dt is equals to 1 divided by rc into yt plus 1 divided by rc into yt is equals to 1 divided by rc into xt. So this is our equation. This is our first order constant coefficient differential equation. So this is our first order constant coefficient differential equation. So these are constant. Here constant is 1, here constant is 1 divided by rc, here constant is 1 divided by rc. So this is first order, this is first order constant. This is an example of first order constant coefficient differential equation. This is an first order constant coefficient differential equation. So let us discuss some of the properties of this constant coefficient differential equation. So let us give the numbering. So okay. Okay, there is some problem now in this open board. So basically the equation is dyt divided by dt plus 1 divided by rc into yt is equals to 1 divided by rc into xt. So the general solution, if we solve this equation, then the general solution of equation this linear constant coefficient differential equation is we have two types of solution. One is that particular solution, and another solution is called homogeneous solution. So the general solution of equation 1 for a particular input xt is given by. So the general solution of this equation 1 for a particular value for a particular input xt is given by, it is equals to yt, it is written as yt is equals to ypt plus yht. Now what is yt? So where ypt is a particular solution, is a particular solution, and yht is homogeneous solution. Or it is also called, that homogeneous solution is also called the complementary solution. It is also called the complementary solution, satisfying the homogeneous differential equation. So we have summation. So complementary solution we will get when we have k is equals to 0 to k is equals to capital N ak dk yt, and this is h, we are writing in subscript h, dt and dtk is equals to 0. So basically if this equation is equals to 0, then we are able to get the homogeneous solution. Then we are if the linear differential equation satisfies this property, then we are able to find out the homogeneous solution. So we have the exact form of y, basically the exact form of this yht, the exact form of this yht is determined by capital N auxiliary conditions. So please understand that the exact form of yht is determined by capital N auxiliary conditions, is determined by capital N auxiliary conditions. So let us discuss another property of this linear constant coefficient differential model. It is linearity. So the system specifies the linear constant coefficient differential system will be linear. It will be linear only if all the auxiliary conditions are 0. So if all the auxiliary conditions are 0, then this system is said to be linear. So if the auxiliary conditions are not 0, so there is a possibility that the auxiliary conditions are not 0. So if the auxiliary conditions are not 0, if the auxiliary conditions are not 0, then the response yt of the system, of the system can be expressed as yt is equals to yzit. Please understand, yzit plus yzst. Now what is yzit? So where yzit is called zero input response, and it is the response of the system, and it is the response of the system to the auxiliary conditions, conditions and YZST called the zero state response if the response of a linear system with zero auxiliary conditions. So please note that YZI, please note that YZI is not equals to YHT and YZS. So YZIT, better to write in T, and YZST is not equals to YPT. Okay, so and in general YZIT contains YHT and YZST contains both YHT and YPT. So this is very important point we need to understand. So that system we can write it as the input is xt. So let us write this system. The input is xt and that input is applied to a linear system. The input is applied to a linear system and after that the response the output we are getting is YZST and there is a summation and we are adding this with YZIT and finally we are getting the output YT. So this is our zero state and zero input responses and zero. So this figure is basically the zero state and zero input responses. Please understand. So the third property is that we need to discuss the causality of this linear constant coefficient differential model. So the causality, we need to discuss the causality. So let us discuss the causality condition. So in order for the linear system to be defined by linear constant coefficient differential model, okay, in order for the linear system defined by the constant coefficient differential model to be causal, we must assume that we must assume that the condition of initial rest, we must assume the condition of initial rest, and we can say that or an initially relaxed system, that is xt is equals to 0 for t is less than or equal to t naught. Then assume yt is equals to 0 for t less than or equal to t naught. Thus the response for t greater than or equal to t naught can be calculated as expressed below. So in next page we have to write in next page. So it is equals to basically yt naught is equals to dy t naught divided by dt is equals to dy capital N minus 1 t naught, that is n minus 1th derivative of y naught with respect to dt. It should be equals to 0. So okay, where dk, that is k derivative of yt, and at t equals to c naught, it should be equals to dk yt divided by dt. So basically this we have replaced this t with t naught, and this is basically dk is basically the d raised to the power k is basically the kth derivative of yt with respect to. So first we will find out the kth derivative of yt with respect to t, and then we will put t equals to t naught. Then it will be equals to dk y t naught divided by dtk. Okay, so clearly at initial rest or initially relaxed system, yzit should be equals to 0. Now very important property is time invariance properties. Time invariance property. So for a linear system and also causal system, the initial rest also implies it is very important point. The initial rest also implies time invariance. The initial rest also implies the time invariance. So next property is impulse response. So how to get the impulse response? So basically for getting the impulse response, we have to provide the impulse as input to the linear constant differential equation model. So what we will get? the impulse response ht of a continuous time LTI system is given by replacing xt is equals to del t, and yt will become ht. So we have summation k is equals to 0 to capital N ak d raised to the power k, that is k derivative, ht divided by dt. So we have replaced yt with ht, that is impulse response. So when we have impulse as input, the response we are getting is called the impulse response, and it is xt is equals to xt we have replaced with del t. So this is our impulse response. So and also we assume that initial conditions are present. So we assume that we assume all the initial conditions. All the initial conditions are present. Now let us solve some problem. So the first problem is problem 1. The continuous time continuous time system is shown below. The continuous time LTI system is shown below. So the system is xt, we have input xt, then we have summation, and after that the whatever we are getting is denoted by et, and it is passed through this integrator, and we are getting output yt, and a part of the yt is feedback, and it is multiplied by a constant multiplier. The gain of the constant multiplier is e, and this output is fed back to this summation here. So basically that et is nothing but xt. It is nothing but xt. So this is minus here, I think. Okay, sorry for that. So et is equals to xt minus a into yt. So this is our model. So this is figure 1. This is figure 1. So we need to find out the linear differential equation mathematical equation of linear differential equation. So find linear constant coefficient differential equation. Now let us solve this problem. So the problem is in this problem we have given et. So what is et? So it is basically the input of the integrator. If we see the figure, we can we can see that et is nothing but the input of the integrator. So the output yt of the integrator is nothing but because it is an integrator, so it will integrate et. So it is minus infinity to t e tau d tau. This is equation first. Now we can differentiate both sides. We get dyt divided by dt is equals to et. Then after that we will see that this ET is nothing but xt minus a into yt. Because that ET is nothing but a portion, this portion is fed back again to that input, and that basically we are using that there is a summation symbol there. So basically ET is equals to xt minus a into yt. Now we can use this equation 3 into equation. We can use this equation 3 into equation 2. So what we will get here? So we will get here dyt divided by dt is equals to xt minus a into yt. So basically we have just replaced the value of et. Now we can further write it as dyt divided by dt plus a into yt is equals to xt. So this is our equation number 4. Now if we see that equation, then we can say that if we see this equation, then we can say that it is nothing but first order. It is nothing but the first order linear constant coefficient differential equation. So why I am saying that it is first order? Because only first order derivative is there. That's why it is first order linear constant coefficient differential equation. So let us discuss another problem, and the system is given as the continuous time system is given below. The continuous time system is given below, given in figure 2. So the system is, we have input xt. Now we have this summation symbol. After that we have a scalar multiplier, and whatever we are getting, that is et, it is passed through that integrator. Then after that there is another integrator, and finally we are getting output. There is another integrator, and that output again, this is a2, this is a1. This constant is a1, that first constant multiplier is a1, and the second constant multiplier is a2, and this constant multiplier is connected through this line. Now this is, suppose this is this is omega t and this is et. So in this problem also we need to find out the linear constant coefficient differential equation. So what is et? So it is nothing but the input of the integrator, input of the first integrator. So we have two integrators. So it is the input of the first integrator. Here you have this is your first integrator, this is your first integrator, and this is your second integrator. So it is basically here it is et. It is basically the input of this first integrator, and this wt is the output of the first integrator, and it is basically the input of the second integrator. So it is basically the input of the first integrator, and wt is output of the first integrator. So what is ET? ET is nothing but dWt divided by dt. It is nothing but how it is basically Wt is nothing but minus infinity to t e tau d tau. So after differentiating with respect to t, we will get dWt divided by dt is equals to Et. That's why I have used this relation. So this is our first equation. Then we have we can use that value of omega t. So what is that value of omega t is basically we have this is the input of the basically that omega t is nothing but dyt divided by dt. So how it is coming? So basically we can see that yt is nothing but minus infinity to t w tau d tau. So if we differentiate with respect to t, we will get dyt divided by dt is equals to wt. And also and also the et is written as dWt divided by dt, and it is equals to minus a1, please check, minus a1 omega t minus a2 yt plus xt. Please check this equation, please check. We can see from this figure, we can see here this et is nothing but what we are getting here. We are getting here a2 into yt. What we are getting here, I did some mistake in the figure. Please correct it. Sorry for that. So actually that we are getting feedback of output. Basically we are getting the feedback of output. Sorry. So please check, this is yt multiplied by a2, this is a2 into yt, and what is that what is the output of this scalar multiplier? So the output of this scalar multipliers, please check it again. So it is scale factor a1, so it is nothing but a1 multiplied by omega t. It is a1 multiplied by omega t. So what is et? So et is nothing but your input, that is xt. Then you have a2 minus a2 into yt minus a1 into omega t. This is et. So we can use this relation. So this is equation number 2 and this is equation number 3. Now we can use equation 3 into equation 2. So what we will get by using equation 3 into equation 2, what we will get using 3 into 2, we get d square yt divided by dt square is equals to minus a1 dyt divided by dt minus a2 yt plus xt, or d square yt divided by dt square plus a1 dyt divided by dt plus a2 into yt is equals to xt. So it is nothing but a second order linear constant coefficient differential equation. So if we analyze this equation, so it is nothing but it is second order constant. It is nothing but the second order constant coefficient linear differential equation. It is nothing but the second order constant coefficient linear differential equation. So let us do another problem. So the problem is, consider a constant coefficient continuous time. Consider a continuous time system whose input xt and output yt are related by dyt divided by dt plus a into yt is equals to xt, and where a is constant. So first part is find out yt with the auxiliary conditions y0 is equals to y0, it is given, and xt is equals to k e raised to the power minus bt into ut. The b part is express yt. In terms of zero input and zero state responses. So the answer is, let yt is equals to ypt plus yht. What is ypt? It is particular solution. Let ypt, so what is ypt? It is particular solution. And what is yht? It is homogeneous solution. So the homogeneous solution should satisfy the following condition: dyht divided by dt plus a into yht is equals to 0. If it is satisfying this condition, then we can say that it is homogeneous solution. So this is equation number first, this is equation number second. Now assume that ypt is equals to e raised to the power minus st, where t is greater than 0. Now this is equation number 3. So substituting 3 into 2, we get minus ba e raised to the power minus bt plus a small a multiplied by capital A e raised to the power minus bt is equals to k e raised to the power minus bt. This is equation number 4. So from which we can obtain a. So a we are getting is k divided by a minus b. Please check. And ypt we will get it is equals to k divided by a minus b e raised to the power minus bt. So please check these two equations. and this is equation number 5. Now to obtain YHT, second is to obtain YHT, that is homogeneous solution, what we have assumed. So we assume YHT is equals to B e raised to the power ST. After that we can use 6 into 2, what we will get, so what is second equation? Please check the second equation. So that this is please check the second equation. So this is our second equation. So what we are going to do, we are just replacing sixth equation with second equation. So we are getting it is equals to S del so one minute please. Okay, it is equals to SB e raised to the power ST plus AB e raised to the power ST is equals to S plus A into B e raised to the power ST is equals to 0. So if we have S is equals to minus A and YHT is equals to B raised to the power minus AT, this is equation number 8. Then what is YT? So we have get YHT, that is homogeneous solution, is equal to B raised to the power minus AT. So by solving this, so YT is nothing but YHT plus YPT. It is a sum of particular solution plus homogeneous solution. So if we want to find out the YT, then it is equals to B raised to the power minus AT plus K divided by A minus B e raised to the power minus BT or for t greater than 0. Now from, and this is equation number 9. So this is equation number 9. So this is equation number 8 and this is equation number 7. I forget to mention, sorry for that. So this is equation number 9. So from 9 and auxiliary condition y0 is equals to y0 we obtain, and using y0 is equal to y0 that is given in the question, it is for initial condition is given, we obtain b is equals to y0 minus k is equal to a minus b, that is equation number 10. So using this b in 9th, using the value of b in this equation, we will get yt is equals to y0 minus k divided by a minus b. So this is our final total solution, that is sum of particular plus homogeneous solution plus k divided by a minus b e raised to the power minus bt for t greater than 0. So this is our response yt. Now we can further see that if we have the condition that for t less than, if we have t less than 0, what we have xt is equals to 0, the input is equals to 0, and the expression dyt divided by dt plus ayt is equals to xt become, it becomes dy ht divided by dt plus ayht is equals to 0. So hence yt is equals to b raised to the power minus at for t less than 0. This is the equation number. Okay, so this is equation number 10. So this is equation number 11, and this is equation number 12. So from the auxiliary conditions, we can see that from the auxiliary conditions, we can see that y0 is equals to y0, and finally we get yt is equals to y0 e raised to the power minus at for t less than 0. So this is the equation number 13. Now comes to B part. So we can combine equation 11 and 13. yt can be expressed in terms of yzit, that is zero input response, and yzst, that is zero. So this is nothing but zero input response, and this is yzs, that is zero output response. So yt is written as y0 e raised to the power minus at plus k divided by a minus b. So better to write it is as a minus b. A minus b e raised to the power minus bt minus e raised to the power minus at into ut. Please understand, it is for t greater than 0, that's why. So this part is only for t greater than 0, that's why we use ut. Now what is yt? So yt is nothing but yzit, that is zero input response, plus yzst, that is zero output response. So what is yzit? So where yzit, that is zero input response, is y0 e raised to the power minus at so, and yzst, that is zero output response, it is equals to k divided by a minus b e raised to the power minus bt minus e raised to the power minus at into ut. So this is our solution. Now comes to problem number 4. So this is problem number 4. So I think which problem number? Okay. So this is problem number 3. Now we are going to discuss the problem number 4. Okay. So sorry for delay. So consider the system described by y dash t plus 2 yt is equals to xt plus x dash t. So what is y dash t? It is dyt divided by dt. And what is x dash t? It is dxt divided by dt. So the question is find out the impulse response. Find the impulse response ht of the system. Find the impulse response ht of the system. So for impulse response, we are taking impulse as input, unit impulse as input. So it is h and yt will become ht because it is impulse we are providing at the input. So h dash t is equals to so h dash t plus 2ht is equals to del t plus del dash t. So x dash t is equals to del dash t and y dash t is equal to h dash t and yt is equals to ht. So we have taken all these three terms. So the homogeneous solution H subscript ht to equation 1 is hht is equals to c1 e raised to the power minus 2t into ut. This is equation number 2 and this is equation number 1. Now we can assume that assuming the particular solution HPT of the form, HPT is equals to C2 del T. This is equation number 3. The general solution is HT is equals to C1 e raised to the power minus 2t into ut plus C2 into del t. This is equation number 4. So using 4 into 1, what we get minus 2c1 e raised to the power minus 2t into ut plus c1 e raised to the power minus 2t into u dash t plus c2 del dash t plus 2c1 e raised to the power minus 2t into ut plus 2 into c2 del t is equal to del t plus del dash t. Now what is u dash t? U dash t is nothing but del t because the impulse is nothing but the differentiation of unit step. So what we will get here? We will get c1 plus 2 times c2 if we use the relation u dash t is equal to del t. So we get c1 plus 2 c2 into del t plus c2 into del t del dash t is equals to del t plus del dash t. This is equation number 5. Now we can see that by just comparing that del t coefficient here is 1, here is del t coefficient is c1 plus 2 c2. So c1 plus 2 c2 is 1 and c2 is equals to 1. Then we can find out that c1 is minus 1 and c2 is 1. So this is our values of c1 and c2. Now we can use 6 into 5, so we will get ht is equals to minus e raised to the power minus 2t into ut plus del t. So this is our impulse response of the system. So this is impulse response of the system. This is impulse response of the system.